Hello, welcome to Advanced Composites. Today is the concluding day of the first week of this course. Over last several days, we have received quite a good amount of feedback from all of you, and one question or one point which I did not address in previous lectures was if there are some texts which you may be referring to or which you may want to refer to while trying to learn whatever is being covered in this course. So, I will suggest 3 or 4 different books in the context of this course. The 2 books which you will find really useful, at least in context of this advanced level course, I am going to list them. So, the first one is Stress Analysis of Laminated Composites. So, these are textbooks. Okay. And the author is Whitney. The other textbook which you may find very useful is Stress Analysis of Fiber Reinforced Composite Materials. And the author of this is Hyer, Hyer, okay, Hyer. And of course, you should also refer to these books, but some of the advanced stuff may not be in these books. So, the one is Analysis and Performance of Fibrous Composites, and this is by Agrawal and Brautmann. And the last text is Mechanics of Composite Materials, and this is by Jones. But the first 2 books you will find particularly useful because they provide some more detailed discussion of governing differential equations and their solution mechanisms. Coming back to what we have been discussing, yesterday we just finished discussion on prediction of transverse modulus for composite material. The next logical thing would be at what stress levels do these composite materials break when they are loaded transversely in the tensile direction. So, we are going to talk about transverse strength. Transverse strength. So, what does that mean? And we call that sigma ultimate transverse load in the tensile direction, sigma ut. So, you have a sample, fibers are running in this direction. If I pull it in the transverse direction, then at what stress level this thing is going to break. And it turns out that this value sigma u transverse is dominated by the strength of the matrix material, because it is the matrix which resists the breaking of the composite. The fibers do not play a positive role, actually they create a negative role, because they act as stress concentrators, and as a consequence the material does not fail at this value sigma mu, which is the ultimate tensile strength of matrix, but at a lesser value. So, I am going to divide it by a number called S, where S is the stress concentration factor, and you refer to the introductory course, you will find relations for this factor, or also this value is mentioned in the book from Agarwal and probably also in the book from Jones. So, the point is that in the transverse direction, a unidirectional composite, its strength is determined primarily by that of the matrix material, but it is less than the strength of matrix material, because fibers tend to provide stress concentrations, and as a consequence the overall material fails at a lesser value than it would have failed if it was purely matrix. So, having said that, we move on. We will talk about some other properties, but before we do that, we will discuss as a diversion something more about transversely isotropic materials. So, now that we have become somewhat familiar with this terminology EL, ET and all that, it is probably the right time to talk about what kind of properties transversely isotropic materials have. And to understand that, let us make a simple diagram. So, this is the same diagram which we had made earlier. So, here we have a block of material, fibers are running in one direction only, and all these fibers have circular cross sections, because we are discussing, otherwise the material will not be transversely isotropic. Okay. So, what are the material axes? This is my L axis, this is the transverse axis, and this is the other transverse axis. So, what is the plane of transverse isotropy? Plane of transverse isotropy. It exists in TT plane, TT plane. Specifically, it exists in this plane 1, 2, 3, 4, right, because if I pull or test this material in this plane, then its properties will come out as isotropic, and if that is the case, then we write some mathematical relations based on this understanding that this is transversely isotropic. So, if it is transversely isotropic, then ET is equal to ET prime. Okay. The other thing is its Poisson's ratio mu T prime. What does that mean? That if I pull the sample in T direction, it will experience Poisson contraction in T prime direction. That number is mu T prime. So, that will be same as mu T prime T. Okay. In this case, mu T prime T, I am pulling the sample in T prime direction and the Poisson contraction is happening in T direction. Then G T prime, which is the shear modulus. So, G T prime So, this is T direction, this is T prime direction. So, I am applying like this. So, this is same as G T prime T. So, these are some of the things related to transverse isotropy, and it turns out that mathematically, and we may see some of this mathematics later in the course, mathematically transversely isotropic materials have 4 fundamental elastic properties. So, those are EL, and we already know how to compute EL. The second elastic property is ET, and we already know how to compute ET because using the help and psi relation, and this ET is same as ET prime. The third independent elastic property is GLT. So, we will learn how to compute this, and the fourth one is mu LT, which is the Poisson's ratio, and we will explain what does mu LT mean, and we will also learn how to compute these. So, what we have learned till so far is how to compute EL and how to compute ET. So, the next 2 relations which we will discuss are the relations for the Poisson's ratio and the shear modulus, okay, the shear modulus and the Poisson's ratio. So, let us just look at the relation for shear modulus. GLT. So, if I have a sample and let us say my fibers are running like this, this is my L direction, this is my T direction. So, shear is being applied in the LT plane. So, this is my LT plane and I am applying shear force like this, and because I am applying shear force in the LT plane, I call NF, and the thing will experience a shear strain, then GLT is what is the ratio of shear stress tau LT. So, this is, let us say this force is P, then if I divide P by the cross sectional area, then that will give me shear stress, and if I measure the shear strain gamma LT, then their ratio will be GLT. This is the physical meaning of GLT. So, in this case, so GLT divided by GM equals 1 plus eta times volume fraction divided by 1 minus eta times volume fraction, where eta equals GF over GM minus 1, where GF and GM are shear moduli of fiber and matrix divided by GF over GM plus 1. So, this is the help and psi relation for GLT. Okay. The next parameter we will discuss is Poisson's ratio mu LT. So, first let us understand what this parameter means. So, what this means is that if I have a sample of unidirectional fibrous composite, fibers are running, let us say, in the L direction. So, this is my L direction, this is my transverse direction, and I apply a force here P, and as a consequence of this force it will experience a longitudinal strain, and so it will become a little longer, and it will also contract in this direction. So, it will also exhibit strain in T direction, but that will be compressive, right. So, this is because of Poisson effect. Okay. Then Poisson's ratio LT is equal to negative of transverse strain divided by longitudinal strain. So, that is the physical meaning. So, what does this mean? That L is the direction of load and this T, the second subscript, is the direction of Poisson strain. Okay, this is the direction of Poisson strain. And the mathematical expression, if we want to compute, is Poisson ratio nu LT is equal to volume fraction of fiber times Poisson's ratio of fiber plus volume fraction of matrix times Poisson's ratio of matrix material. So, it is a pretty straightforward formula. Okay. And physically what it means is, we have already shown that this is equal to minus epsilon T divided by epsilon L for the situation where force is being applied in the L direction. Now, you may wonder, what about nu TL? Okay. So, physically what does that mean? What it means is that suppose you have a sample and fibers are in the transverse direction. So, this is the longitudinal direction, this is my transverse direction, and I am applying a load in transverse direction, because the first subscript is T, which means the load is being applied in transverse direction. Then because of this, the primary strain will be epsilon T and it will be tensile, and the secondary strain will be epsilon L, it will be compressive and it will be due to Poisson effect. And then nu TL is equal to minus epsilon L by epsilon T. And how do you compute it? So, nu TL is equal to, and this can be shown mathematically, that this is equal to nu TL is equal to nu LT times ET divided by EL, ET over EL. So, what we have discussed till so far are several different elastic properties. We have learned how to calculate EL, how to calculate ET, mu TL, mu LT, GLT. And last couple of minutes I will spend talking about different strengths of unidirectional composite materials. So, at a fundamental level, there are 5 independent strengths of unidirectional composites. So, 5 independent strengths of unidirectional composites. Okay. What are those? So, first one is sigma UL. It is ultimate tensile strength, it is tensile strength in L direction. Okay. Then there is another strength, sigma UL prime, and this is compressive strength in L direction. Then similarly we have two strengths in transverse direction. So, sigma UT, it is tensile strength in T direction. Then similarly we have sigma UT prime. So, this is the nomenclature we will use, so we should be familiar with. So, that is compressive strength in L direction, and the last one is tau LT. I am sorry. So, this should be T direction, and the last one is sigma ULT, excuse me, it is actually shear. So, tau. So, this is shear strength in, and here we do not talk about direction, but we say in the LT plane. Okay. So, if we know these 5 strengths of unidirectional fibrous composites, then we are well equipped to predict their failure when they are subjected to external stresses or strains. So, that is what I wanted to discuss in today's class, and this also concludes pretty much most of the stuff which I wanted to cover related to properties, elastic properties of composite materials. Next week we will move in a similar direction, but we will quickly graduate to prediction of stresses and strains in generally orthotropic material, that is when the stresses, external stresses and strains and external loads are not necessarily aligned to the material axis of unidirectional fibrous composites. Thank you, and I look forward to seeing you on day after tomorrow, that is on Monday. Thank you. Bye.